We're given the graph of the function f in the figure below. G is the integral from negative 6 to x of f of t dt. And we want to determine all the values where g has a point of inflection at the open interval. So in order for g to have a point of inflection, the second derivative needs to go from positive to negative or from negative to positive. So that leaves us to find the second derivative. Well, if g of x is defined to be the integral from negative 6 to x, f of t dt, the derivative of g is just lowercase f of x, and so the second derivative of g will just be the first derivative of f. Okay, so we can replace g double prime with f prime. So we're looking now at the graph of f, and we want to consider the derivative of f. So from negative 9 to negative 6, this is a line with slope negative 2. So the derivative here is negative 2. And then from negative 6 to negative 1, this is another line with slope 1, so the derivative is 1. Okay. So it doesn't matter what the actual value is, as long as it's changing sign from positive to negative or negative to positive. And so from negative 1 to 2, here the slope is positive, it's increasing, so the derivative is positive. But then from 2 to 5, the slope is negative, so it's decreasing, and same thing from 5 to 9. So we need to see now where the sign changes. So if I can replace the negative 2 with a negative, the positive 1 with the positive, we see clearly at x equals negative 6 that this is a point of inflection, since the second derivative changes from negative to positive. Now, the point at negative 1, well, it's positive from the left, positive from the right, so we're not going to include that. At 2, from the left it's positive, from the right is negative, so we want to include x equals 2 as a point of inflection. At x equals 5, it goes from negative to negative, so that doesn't change anything. And so we conclude by saying that the point of inflection for g occurs at x equals negative 6 and 2.